Imagine a world where the global supply of precious metals is no longer tethered to the Earth's crust. Suddenly, a new and seemingly endless stream of raw materials begins to arrive, not from deep pit mines or remote terrestrial deposits, but from the darkness of space. Tons of platinum, iridium, gold. This isn't a trickle. It's a steady, calculated flow, the result of robotic missions successfully capturing and processing asteroids. The immediate outcome is a fundamental disruption of value itself. The scarcity that has defined human economies for millennia is abruptly challenged, creating a shockwave that ripples through every financial system on the planet. This new reality introduces an unprecedented variable into our global resource equation, forcing us to rethink everything. This dramatic shift establishes a complex problem space. How does a global economy, built on the finite nature of terrestrial resources, adapt to a potentially infinite supply from beyond? The arrival of these materials creates immediate questions about ownership, control, distribution. National economies that rely heavily on mining face an existential threat, while new corporate and state actors emerge to dominate this new frontier. The central challenge is not one of technology alone, but of systemic adaptation. The existing frameworks governing international trade, property rights, strategic resources are rendered instantly obsolete by a resource stream that originates outside any sovereign territory, challenging the very foundations of geopolitical power and economic stability. The key participants in this new arena are not just the traditional mining conglomerates or national space agencies. A new ecosystem of players quickly materializes: venture-backed aerospace startups, tech behemoths, governments, and geopolitical blocs. The stage is set for a high-stakes competition where the winners will redefine the global balance of power for centuries to come. This scenario forces us to ask a central, system-defining question. How would a consistent and growing flow of space-derived metals and volatiles fundamentally change our global resource systems? It's not just about cheaper materials, it's about the mechanisms that would govern this new economy. We must explore how markets would price these new assets. Existing supply chains would be rerouted or abandoned. What new infrastructure would be required to support this celestial industry? The introduction of asteroid resources is not a simple addition, but a catalyst for a complete rewiring of the world's economic and political architecture, triggering feedback loops that are difficult to predict and even harder to control. To understand the mechanics of this transformation, we must visualize the operational pipeline from start to finish. The process begins with advanced detection systems, a network of space-based and terrestrial telescopes constantly scanning the skies for suitable near-Earth objects. Once a viable target is identified based on its composition and trajectory, a robotic rendezvous mission is launched. This craft is designed for a singular purpose: to autonomously intercept the asteroid, to anchor itself, to begin the extraction process. This initial phase is a delicate dance of orbital mechanics and precise engineering, where timing and fuel efficiency are the primary constraints, dictating which targets are economically feasible and which remain out of reach for now. The core of the operation lies in the extraction and processing mechanism. Early-stage models favor a straightforward approach. Robotic excavators drill into the asteroid's surface, extracting raw ore, rich in platinum group metals, iron, and nickel. This material is then heated in a simple onboard refinery, separating the valuable metals from the silicate rock. The refined payload, now a dense metallic ingot, is packaged into a specialized re-entry vehicle for its journey back to Earth. This initial blueprint prioritizes simplicity and reliability over maximum efficiency, establishing a baseline for the first wave of commercial-scale resource returns. The entire system is a closed loop, from detection to final delivery. However, we must acknowledge the inherent limitations of our current technology, which place significant constraints on this nascent industry. The cost per kilogram to launch anything into orbit remains a formidable barrier, heavily influencing mission design and profitability. The energy required for in-space refining is immense, creating a critical trade-off between the mass of processing equipment sent and the potential yield returned. These constraints mean that only the most valuable, easily accessible asteroids are targeted in the beginning. The system is designed to be incremental, starting with high-value, low-tonnage missions that can prove the economic model before scaling up. As we look beyond these initial commercial-scale operations, our predictive models begin to diverge significantly. The central point of uncertainty revolves around the long-term strategy for processing. One path, return refined materials to Earth, keeps economic gravity on the planet but is limited by re-entry costs. Alternative path, process and utilize resources entirely in space. Orbital manufacturing hubs and refueling depots. The choice between these two futures depends on complex feedback loops involving launch costs, market prices, and technological breakthroughs, and it is at this threshold that the system's future behavior becomes profoundly uncertain. Today, our global commodity markets operate as a finely tuned yet fragile system. The prices of platinum, gold, and other precious metals are determined by supply from terrestrial mines and industrial demand. This entire structure is built on scarcity. The cost to excavate these materials from the Earth's crust sets a fundamental price floor. But we are in a battle against diminishing returns. The most accessible deposits have been exploited, causing costs to rise. It is this rising cost floor that creates the economic incentive for looking to the stars. The single greatest constraint on any off-world enterprise is the cost of escaping Earth's gravity. While reusable rockets are lowering prices, the cost remains a dominant factor, forcing a relentless trade-off between capability and mass. Beyond launch costs, orbital mechanics dictate the rules. Intercepting a fast-moving asteroid requires a specific change in velocity, known as delta V. This is the celestial equivalent of fuel economy, determining which asteroids are accessible. The industry's viability hinges on lowering the cost to leave Earth and increasing the efficiency of traveling through space. Before mining begins, asteroids must be found and cataloged. A global network of telescopes analyzes each discovery for its orbit, size, and composition, creating a database of potential targets. Choosing a target is a trade-off between reward and risk. But from identification to launch, mission planning and regulatory approvals create a formidable delay of 5 to 10 years. This inherent lag is a critical stabilizing mechanism, preventing a market gold rush and allowing for a slow, predictable supply of new materials. The moment the first commercial re-entry capsule lands, the global commodity market enters a new state. The impact is informational, a confirmed signal that a non-terrestrial supply chain is now an operational reality. Spot prices for platinum and iridium plummet, not due to the initial quantity, but the market's recalculation of future scarcity. The ripple effect moves swiftly to the physical world. As prices fall below the cost of extraction, mines become unprofitable. This creates billions in stranded assets, specialized equipment, and entire mines rendered worthless. Entire towns built around these operations face collapse, triggering severe regional economic distress and social unrest across the globe. As terrestrial mining nations face fiscal crisis, their first response is defensive. They impose export controls and attempt to form cartels, but these are powerless against a new supply source outside their control. Simultaneously, spacefaring nations become gatekeepers, instituting re-entry tariffs and orbital licenses, a new resource nationalism. Space elevates to a critical arena of national security. Naval fleets are dispatched to secure recovery zones for the billion-dollar capsules, creating a protective shield. An attack on these assets is an attack on the state itself. In the long run, the chaos of the initial transition settles into a new, stable equilibrium. The initial ISRU model, producing propellant from water ice, creates a network of autonomous refueling depots. These gas stations in space fundamentally alter mission economics, increasing reach and payload capacity. Rather than returning refined metals to Earth, it's more efficient to process raw asteroid materials in space. These materials become the building blocks for a self-sustaining industrial ecosystem. This enables orbital construction of massive structures like solar power satellites and deep space telescopes. Section 2. An open loop. Despite this newfound stability, the system operates with critical, unresolved tensions that leave the long-term future an open cognitive loop. The legal framework for the celestial commons is fragile and contested. The worsening debris problem threatens a runaway cascade of collisions, and with no overarching authority, who pays for and manages public goods like space traffic control remains unanswered. The stability of this new world is contingent on remaining below critical but poorly understood thresholds. The great challenge is not just to operate within this new reality, but to measure, monitor, and manage the hidden thresholds that govern it. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.